So if you look forward a couple days in the lecture note, you'll see something, or on the website, you'll see something called Basic Electric Field Geometries. That's what we're going to prove today. So we're going to do the electric field from a point, which we actually just did. We're going to do the electric field from an infinite line, and we're going to do the electric field from an infinite plane, all in using very basic algebra, no calculus, in a very short amount of time. You ready? The trick is always trying to get your Gaussian surface drawn properly. All right, so remember when I said there's this certain thing about symmetry that you have to deal with? Like, what is the symmetrical shape, like a sphere? You can always draw a bigger sphere around that first sphere, and if you draw it that way, the E field lines are always perpendicular to the sphere, no matter how big you draw the sphere?
Yeah.
All right. And then I said the sphere, the coaxial cylinders, and the planes can all have, it is always possible to draw another one such that the E field hits the second one perpendicular to the surface, right? Or normal to the surface. All right, so we're going to start with an infinitely long charged line / rod / wire / whatever. What Gaussian shape would you draw for a line of charge such that the E field always hits the surface perpendicular to the surface?
Cylinder.
You draw a cylinder on the outside, right? So here's your cylinder that we drew. Okay, good? Now we're going to draw that cylinder a certain radius away from the center. And we're going to use Gauss's law to determine the electric field strength at that particular radius away from the center. Does this make sense so far?
Yeah.
So we're trying to figure out the electric field strength, but we're going to use Gauss's law to do it. So here we go. We make the statement that the total flux through this cylinder is equal to the charge enclosed by the cylinder divided by epsilon naught, right? All right, so here we go. How many surfaces are on this cylinder?
One.
No.
Oh, three.
Three. There's the left side, the right side, and the lateral area of the cylinder. Does that make sense? Circle here,
The top and bottom.
and the lateral area. Well, no, remember, Gauss's law always has to be a closed surface.
What's connected, but what if you
A
hold
Gauss's law is only true for a closed surface.
so you're like through the thing?
Yeah, the wire punches its way through this closed cylinder. Yes.
So does other people like cargo wires and not get all the electric field that's activated for the phone?
Oh, you mean for the whole entire infinite wire?
You'd have infinite charge.
Yeah, if you had an infinite Gaussian cylinder, yeah, you'd have an infinite amount of charge to enclose, and then you'd have infinity over infinity and all sorts of nastiness associated with that. So we're not going to include, that's actually a really good question, and it's a common conceptual thing that people don't understand. The Gaussian surface that we're going to draw is never going to be an infinite surface. It's always going to be of a finite length. Otherwise, it gets really confusing because you're enclosing infinite charge. All right, so yeah, we're going to take a piece of Gaussian surface that's got a length of L that's going to enclose, you know, L of the wire, of this infinite wire. All right, so it's got two end caps and it's got the lateral area, right? All right, so we know the flux through the lateral area plus the flux through the ends has to equal charge enclosed over epsilon naught, right? How much flux is going through the ends?
0.
Why 0?
Because the angle is.
Yeah, because any field coming out is running parallel to that end. It's not actually going through it. All right, so the only actual flux that you have to worry about is the flux going through the lateral area of the cylinder. Good so far?
Yes.
All right. Now, the flux going through the lateral area of the cylinder is the electric field times the area, right? So the electric field is what we're looking for. What's the lateral area of this cylinder?
2 pi r h.
2 pi r
L.
L, right? You guys remember how to do that? So it's E times 2 pi r L equals charge enclosed over epsilon naught. So what's E equal to?
Q over 8 epsilon.
Charge enclosed divided by L times 1 over 2 pi r epsilon naught. Or in other words, charge
Density.
per length is charge density divided by 2 pi r epsilon naught. And that should match what you had previously. No calculus required, no limits, no L'Hopital's rule, none of that garbage. In essentially one simple algebra step.
So flux A is the electric.
No, the flux is the electric field times the area. But the area is area of a cylinder. Got it? All right, simple? All right, let's do a different shape. Infinite sheet or plane. We pretend like we have an infinite sheet of charge, this kind of trapezoid? Rhombus. No. Yeah, that shape. Parallelogram. This parallelogram shape right here is representing an infinitely large sheet of charge, of positive charge. Good? What way does the field go from it? Out in all directions, right? Now, what shape do you think you would draw that would enclose an infinite sheet of charge such that the electric field lines are either perpendicular or parallel when they cross the surface? Well, I say we draw an end cap here, an end cap here, and we enclose it, we make like a cylinder shape. All right? And therefore we know how much charge, the charge enclosed is going to depend on how much, whatever the cross-sectional area of that cylinder is. Does that make sense? Or technically a circular prism. Actually, it doesn't really matter what shape you pick, just as long as you could have picked a square here, just as long as you know the area. Good? All right, so here we go, and this one is tricky. We choose a cylinder or some sort of rectangular prism with end plates that are parallel to the charged plane. Good so far? Now, we know if this is our Gaussian surface, this little cylinder here, that the total flux through its surfaces is equal to whatever the charge is enclosed, divided by epsilon naught, right? So let's figure out the total flux first. How many surfaces does this cylinder have? 3. Is there any flux on the left end cap?
Yes.
Yes. Is there any flux on the right end cap?
Yes.
So there's flux through the left and right ends.
Yes.
Is there any flux through the lateral area?
No.
Why not?
Because it's perfect.
Because it's, yeah, it's running kind of parallel to those field lines. Okay. So the only thing that matters is the two ends, but we got 2 of them. We've got an end on the left side and an end on the right side. So the flux through the ends is going to be 2 times the electric field strength times the area of each end cap. Plus 0, because the flux in the lateral area doesn't matter. So 2EA equals charge enclosed over EA, or epsilon naught. Which means the electric field equals charge enclosed over 2A epsilon naught. Or in other words, electric field is equal to the surface charge density over 2 epsilon naught. Done. Got it? Which is way quicker than trying to figure this out with Coulomb's law. In fact, Here's a little secret about Gauss's law. Physicists consider Gauss's law to be a more fundamental description of the universe than Coulomb's law. It's considered to be more generally applicably true than Coulomb's law, for reasons we're going to talk about at the end of the year. All right? Gauss's law is better on so many levels than Coulomb's law. All right? You learned Coulomb's law first last year because it's an easy way to describe what happens with point charges. Gauss's law is way more powerful in the end. All right? And you're just getting a little glimpse of how powerful it can be, because you can solve an infinite sheet, which would have taken a lot of integration using Coulomb's law. You can solve it in one step with very simple algebra with Gauss's law. Yes? You would not have been able to use Gauss's law simply, because you would have had to have chosen some Gaussian surface, or because these lines would have bent out towards the edges, right? Like, you see? So you either have to choose a Gaussian surface that would have been perpendicular to all those field lines, so you didn't have to deal with the cosine theta, but then your electric field strength is changing. Or, yeah, you would have had to have figured out what, at every single area of intersection, what the electric field is and what the direction of the cosine theta would be. And it's changing constantly. So Gauss's law is really simple only for infinite shapes. Good? All right. So we just talked about how to do the electric field from an individual plate. What if you have two parallel plates, like a capacitor? All right? How would you use Gauss's law to determine the field inside and or outside a capacitor? Did you do this in class before?
I think we did something.
Well, we did it in here, where I used superposition and Coulomb's law. But we're going to do it with Gauss's law now. All right. So, let's say you wanted to figure out what the field is inside the parallel plates. Oh, by the way, what's the field? If these are charged the same, have the same charge density, what's the field out here?
0.
Why is it 0?
Because all the charge is being transferred from one plate to another.
What? There is no charge transferring in this picture.
The field is
All right. If the negative plate weren't here, the field would be whatever it would be because of the positive plate, right?
right.
Now, if you had and that field wouldn't get any weaker, right? But if since the negative plate is here, the field from the positive plate is going to perfectly cancel the field from the negative plate on the outside. Therefore, the net field is going to be 0. Now, what if the positive plate had more charge on it than the negative?
Then it would be more positive.
Then the net field would be to the right. Does that make sense?
Yeah.
All right. So, yeah, just as long as the plates have the same charge density and they're infinite, the field on the outside is going to be 0. Yes?
You know how, like, for an infinite plane, like, even if it's like 1,000 miles away, it's the same strength field.
Yeah.
And you know how, like, even for a finite plane, if you do it like from the distance in the middle,
Mm-hmm.
and you do it like from there, it's still the same thing. That's like the only point where like the field doesn't get weaker. Because like in the middle, it cancels out. You know what I'm saying?
Okay, so,
So if you had like a finite plate,
yeah, finite plane.
charge it up a lot, and then
Yeah.
it would still affect stuff like thousands of miles away.
Well, think about that. You could do this as a problem. You could actually use the equation. And what you discover, as the distance from the plates gets very, very big compared to the height of the plate or the radius of the circular plate or whatever, you would find that it starts looking a lot like a point charge. Remember how we did that problem a few days ago? Or is it, Is like the equation looks more and more like KQ over R squared because the other term just goes away. Yeah. Yeah. It just looks like a point charge. All right, so here we go. So I want to know what the field is between the two plates. Let's pretend I didn't know that the answer was eta over epsilon naught. All right, so here's what I do. I draw a Gaussian surface such that one of the surfaces is on the inside of the two parallel plates, such that the electric field penetrates one of the Gaussian surfaces. All right? Then I've got one here, and one there. All right, so I've created a box with one side of the box having field going through it. What about all the rest of the sides of the box? Is there any field going through this side?
No, you zero.
No. Is there any field going through this side?
No.
Even for the part that's inside the field?
No, because it's parallel to the field lines.
It's parallel to the field lines, right. What about this side?
Parallel to the field
It's also parallel to the field line. So the only side that actually has field going through it is the inside of the box, this one. Good? All right. So the total flux through this thing is going to be only due to this end piece right here. All right? Up. Therefore, the area of this little piece is A, the electric field at that little piece is E, has got to equal charge enclosed over epsilon naught. Therefore, the electric field is going to be charge enclosed divided by area over epsilon naught,
Wait, that's eta.
which is eta. Done. So the electric field inside of an infinite capacitor is eta over epsilon naught. Done. Isn't that cool? No calculus. In fact, I would argue that's about as simple as algebra as you get.
It's pretty difficult.
Any questions? So the hardest thing about Gauss's law isn't any of the math, it's just drawing your Gaussian surface appropriately. And here's a hint. You only have to know 3 of them. You have to know a sphere. You have to know how to draw a surface for an infinitely long cylinder. And you have to know how to draw one for an infinite plane. This one right here. And the infinite cylinder and the infinite plane actually look similar. It's just this one is going through the lateral area and this one is going through the end caps. Does that make sense? All right, that's it for today. We're gonna pick up where we left off and do uniformly charged insulating sphere, which is one of the major applications and gonna be one of your biggest headaches over the next 2 weeks. We're gonna do it tomorrow. That's it.
You're ever gonna show us the